Welcome back to day 4 of Advent of Code, where we find out how much coffee Chris has had today and whether it will affect his mental acuity solving the problem. Got about 10 to 15 seconds until the problem opens. I've already set up our project for today, same setup as usual, so we can get right into it. 3, 2, 1, and we're ready to go. Alright, so I find this easier to read when it's smaller, so I put it on half the screen. Day 4 is camp cleanup. Space needs to be cleared before the last supplies can be unloaded from the ships, so several elves have been assigned the job of cleaning up sections of the camp. Every section has a unique ID number, and each elf is assigned to a range of section IDs. However, as some of the elves compare their section assignments with each other, they've noticed that many of the assignments overlap. To try to quickly find overlaps and reduce duplicated effort, the elves pair up and make a big list of the section assignments for each pair, which are our puzzle input. So Elf 1 and Elf 2, I suppose. For the first few pairs, this list means within the first pair of elves, the first elf was assigned 2 to 4, that is 2, 3, and 4, not 2 and 4, while the second elf was assigned 6, 7, and 8. So these are ranges. The elves in the second pair were each assigned 2 sections. The elves in the third pair were each assigned 3 sections. One got 5, 6, 7, while the other also got 7 plus 8 and 9. Okay, all they're saying is that these ranges are either like 2 or 3 each. Here's one that's 4, 3, 4, 5, 6, 7, or 5 of them. So the ranges vary, but and also some of the ranges are just one value. So let me take this test input and drop it into our test input area here. So what do we actually have to do? This example list uses single digit section IDs to make it easier to draw. Your actual list might contain larger numbers. Okay. Visually, these pairs of section assignments look like this: 2, 3, 4, 6, 7, 8. Okay. Some of the pairs have noticed that one of their assignments fully contains the other. For example, 2 to 8 fully contains 3 to 7, and 6, 6 is fully contained by 4 to 6. In pairs where one assignment fully contains the other, one elf in the pair would be exclusively cleaning sections. Their partner will already be cleaning, so these seem like the most in need of reconsideration. In this example, there are 2 such pairs. And how many assignment pairs does one range fully contain the other? Can we do contains on ranges? So I'm just going to take a look at the docs real quick and see, like, contains allows us to pass in a generic argument u, and it looks like it has to be the type of the item. So we have a range from 3 to 5. We have like u size from 3 to 5. Then we have to pass in a u size, not a range of u sizes. But I also don't know if that's true. They are continuous ranges, so like 2 to 3, 4 to 5, 3 to 7. So we could just check the start and the end for each of them. We don't even need to turn these into ranges. I love that E does a struct in here. Let's see. So we could turn them all into ranges. We could go with start bound and end bound. Contains is still just a U. I don't think we're getting off easy with this. I don't think we're getting a range dot contains other range, although it is really easy to test that. We could do let 1 equals 3 dot dot 7, let 2 equals 4 dot dot 5, and then debug 1 dot contains 2. And this is in Rust Playground. If you've never used that, ooh, I have the layout horizontally, or rather vertically. So you can change the layout. We can't do this, I don't think. It says consider borrowing. Yeah, can't compare integer with range. So that's not possible for us. So I think we do actually have to implement it. We aren't going to get away easy. I do think that we're only going to need the starting and the ending number. Actually, we are going to need ranges here because we're going to need to test to see if one is in the other. And that's much easier for us to do with ranges because we could do 6 dot dot 8 dot contains something else. And if it contains the lower bound and the upper bound, then we're good. I wonder if this is a good day to start using nom. I think it is. I think today is going to be a good day to start using nom because we've already gone over the splits. So if you want to split and iterate and or index into, then the last 3 days, go watch one of those videos. We do that every day. But nom is a parser combinator library. Interesting things about the parser combinator library is that nom is really good at doing like 0 copy parsers. So I think we'll use nom today. Cargo add nom, just to expose you to something that you might not have seen before. So instead of doing manually splitting on comma and manually splitting on dash, we are going to write a nom parser using the nom crate. So really what I'm going to start off with is copying in this example code, because this example code is basically going to set us up for success here. I guess I'll go over it for a second. So we've got basically a parser, right? This example parser in the docs parses a hex code. So you need to parse, for example, an octothorpe or a hashtag or whatever you want to call that. And then you need to parse up to 6 hexadecimal represented numbers. And this parser is a function called hexcolor that takes an input and returns something called an iResult. iResult is a special type inside of nom. And the way the parser combinator library works is that you have these functions that represent what kind of input you want to accept. So for example, this is tag, which looks very specifically for a hashtag character. You pass the input to that function, and then you use the question mark to either return an error. So if it didn't find that hashtag, it would return an error. If it does find the hashtag, then it returns the rest of the input and whatever you matched on. In this case, we match on the hashtag, so we kind of just throw out the second value. But then you can take the rest of the input and you can do something like tuple, and you can define your own functions. So you can say, get 3 hex primaries, and you can combine those functions with a combinator like tuple, which is just another function. And then you can pass the input again, and it will give you the rest of the input, which at this point should be an empty string. And then you'll get red, green, and blue out of it, at which point you can construct your struct or whatever you're trying to parse out, and you can return the rest of the input, which will be, in this case, an empty string. And you can see how this works in the main function down here. This is just an assert equals, so it's like a test. Hexcolor parses this hex, and then the result we get back out of that is an OK with empty input, so nothing left in this string, as well as the color struct with the parsed out numbers. So in our case, we have this over here. So we've got number dash number comma number dash number. And I think we'll return range A and range B, probably just in a tuple. So let's get rid of this starter. And this isn't going to be a hex color. This is going to be what, section assignments. And our success value is going to be a vec of, I guess, tuples, right? Which are going to be ranges. I'll import range. We also have to import iResult, which I think nom has a prelude. I forget if it is, yeah, okay. So I think we can just do nom star for now, and all of the nom stuff will come in. So let's get rid of this stuff. Let's ignore the fact that we don't have any working parsing yet, and let's return an empty vec here. And the input is going to be a string slice that came in, so we'll be good there. Arrange in Rust, of course, needs us to define the index type. So let's go with a U32 maybe. Should be plenty big. So we've got this scaffolding that is basically just saying, we've got the section assignments function that is going to be our parser. We've got some input that's coming in, which gives us a string slice. We are going to return an iResult, which is just a custom like result error type. It's a little bit fancy to go over today, but suffice it to say for now that the string slice is the rest of the input type, which in this case matches our input. And then the second type here is the successful return type. So the thing that we successfully parsed. You can also put a third type in here, which would define the type of the error that you want to return, but we're not going to get that complicated today. So I'm probably going to make 2 functions here, one of which is going to be a parser just for each of the ranges, and one of which is going to be a parser that does a full line, and then we're going to combine that into a parser that does the entire input. So we'll call this sections. It's going to take a string slice, just like everything else that we do with nom. Although you can do byte slices with nom as well. And nom is really fancy. You can also write streaming parsers and stuff like that. But again, this is kind of like an introductory look at nom, so we're not going to get that complicated. So we've got sections that takes an input string slice and returns a range. That means we need to have first a parser for a number, then a dash, and then a parser for another number. So our return type here is going to end up being the rest of the input and what I'll call section range here. We haven't created section range yet. So I already know what parser I want to use, but it will be useful look at a couple of these sort of modules that nom exposes and sort of show you how to find some of these things. So if we click on the number module, there's complete and streaming. In this case, we don't have any streaming requirements. So we're going to go with complete, which is a little bit simpler to work with. And you'll see that there are F32, F64, I8, etc. in here. We're going to go with something like a U32. So right here we have U32, which you can see is a parser. The built-in parsers are written a little bit more in a complicated way to be a little bit more generic and stuff. But a U32 recognizes an unsigned 4-byte integer, which is great for us because that's exactly what we need. So let input, comma, start equals U32 input. And unless this U32 is probably conflicting, because of course we could be referring to like the U32 type in Rust, which is a primitive type, and it is the built-in type that that Rust thinks we're trying to use here. But really what we want is nom number complete U32. So let's just fully qualify that. Of course, number complete U32 doesn't take input. It takes the endianness of the number that you're trying to parse. And of course, as I'm writing this, I'm remembering that the one that's going to be easier for you all to understand is going to be the one from character complete instead of the one that makes you specify endianness. So I'm going to switch to nom-character complete U32, which will still give us that U32, but does it in a way where you don't have to think about whether you're on a little endian or a big endian system. And endianness, of course, is just which of the most important bytes is first. But it's always nice to not have to think about that if you don't need to think about that. So I switched to nom-character complete U32, which you can see with the full module path right here. Of course, that parses this input and gives us the rest of the input. So we'll have -4, comma, whatever, whatever. So we need to let input start. All of these functions return this tuple. So you'll always return this input plus the thing you parsed out, input plus the thing you parsed out. And we're just going to completely shadow this every single time we do that. So let input start equals tag dash, and then we call the input. We also want to handle the errors. I guess we didn't import tag. We'll go with nom bytes complete tag because we aren't streaming. So you can see nom bytes complete tag in the import. And then we need to do this exact same thing right here again to get the second number. And what we get here is start dot dot end. Of course, what I did is I copied and pasted and I didn't change the names. So we've got start and end, and this is going to be dot dot equals because we want an inclusive range. So we want not just 2, but we also want 4 in this sequence. So you can see that our code is compiling now. Did I not save this? There we go. It is saying that we're passing back range inclusive, which is true. So we'll just live with range inclusive for now, which we can also import. So the function sections that we just wrote takes an input as a string slice. It uses the U32 parser to parse out a U32 from the input. We redefine input to be the rest of the input. That is the return value from this function, because this function returns a tuple that we are destructuring. And start is going to be our U32. So we can see string slice U32. We do the same thing. Tag is just an exact match. So we match on the dash, pass the input in, handle the error. We throw away the result because we know it's a dash. This is the rest of the input. Then we do the same thing with the U32. The module paths make this a little bit less readable than I want it to be. So I'm going to come up here and I'm going to put character complete inside of the use item. And then we're going to shorten this to complete U32. So now it's just 3 lines right in a row. Of course, because we're returning range inclusive here, we will also return range inclusive here, because that will eventually be a function that we use. So I'm just going to call this parser line because that's what I want to call it, because it's going to parse the line for us. So this is actually going to return us the tuple representation that we need. Of course, the return value is going to be the input, and then I'm going to call this start and end. And what we're going to do here is take so this is the key point of using nom for parsing, right? So first of all, we're passing string slices all the way around. If we wanted to, we could use string slices absolutely everywhere and make this a 0 copy parser. We're not really concerned about that right now. But because we defined this parser sections, we can use sections now. So let input, comma, start equals sections input. And then let input start equals tag, comma, input, question mark. And let input end, let's get rid of this middle start. I keep doing that. Input end equals sections input. Handle the error. And that's it. So we wrote a function that could parse a range out. We used that to construct a parser for the entire line, which is a really nice abstraction here. And then what we need to do down here for the section assignments is include the new lines. So we can let input, I don't know, what are we going to call this? Ranges? uh, Equals many one input or many one, what did we call this? Line? No, we're not going to use many one. What we're going to do is there's a different one. There's one called separated by. So I'm going to look for separated by, or maybe I misspelled it. Maybe it's separated list. In any case, it's in the nom multi module. So we have a number of things here like count, and these little Alex symbols tell you whether you can use these functions in situations without the allocator. So no standard or embedded scenarios. There's fold many, there's length count, there's many 0, which is what I was going to use, but I don't actually want to use because what I really want is a separated list. And what separated list does is there's separated list 0 and separated list 1. Both of them alternate between two parsers to produce a list of elements, but separated list 1 will fail if the parser doesn't produce at least one element. So what I want is separated list 1. We'll click into separated list 1 and we'll see how to use it. So it's separated list 1. You pass in a parser that is the separator, and then you pass in a parser that is the value, and then you pass in the input. So the separator here is going to be new line, which is also a parser in num, followed by line. We're going to give it the input. We're going to handle the error. Now, separated list 1, of course, is not imported, so we're going to import that. New line is not imported, so we're going to import that from nom character complete new line, and then we're going to return ranges here. So now what we can do is take section assignments, pass in the input. We're going to unwrap this because it's going to succeed for us. And we're going to do let underscore because we don't care about the input assignments equals our parser. And now what we have is a vec of all of the ranges in tuple pairs. And we can prove this by doing debug assignments. And of course, we need to now run the test. So let's start running the test with cargo watch instead of just doing nothing or whatever. And you can see that in the output, we get 2, 4, 6, 8, 2, 3, 4, 5. Let's go see if those are the right numbers. 2, 4, 6, 8, 2, 3, 4, 5, 5, 7, 7, 9. So now we've got a vec of these tuples of these ranges, and we've done it in a fairly, in my opinion, understandable way. It's a little weird to get your head around at first, but the reason this is called a parser combinator library is because we get to use these parsers and combine them to create larger, more complicated parsers. So this sections parser will parse us a range. We pass in the input as a string slice. It returns us a result with the input, which is, or the rest of the input, which is the rest of the string slice, as well as a range inclusive that we've parsed out. We use the U32 parser from the complete module. We handle the error with the question mark, which goes into the I result if it errors out. We pass the input. We get the rest of the input plus the value that we parsed out. And we do it over and over. And then we get to return the rest of the input that is left, plus whatever struct that we wanted to construct here. So sections gives us a range, line gives us both of the ranges, and actually now that I'm thinking about this, this could be tuple, I think, but I'll leave it as sections tag sections. Or separated pair is a good one too, now that I'm thinking about it. Let's do that, because I think that that will be interesting as well. So nom sequence is another module inside of nom. There's things like delimited or pair. Pair would be good if you could get, say, one parser and then another parser right after it. Or preceded is another one where you match some prefix and then you discard it and then you run your parser and get that result back. But in this case, we're going to use separated pair. So first separated second. And this is going to be separated pair. This is going to be sections. And I think it wants a parser as the second argument. So we can do sections, we can do tag, comma, sections, input, and then we get rid of those two. Separated pair, of course, is not something we pulled in yet, so we import that from nom sequence. This is going to be a tuple return type now, so it's going to be start end, and that's it. So now we have separated pair. Of course, we could do the same thing if we, let's say, copied and pasted this and dropped it in right there, and we weren't handling input automatically. So you can just kind of like combine these functions in any way you see fit, and it should work. I'm going to leave it back up, separated out, because I kind of like having it separated out a little bit more. But yeah, that's it. So you build up these functions, you combine them into larger functions, you combine them up until you get to the point where you've parsed out the entire thing that you need to parse out. So big detour into our first usage of nom. Of course, you can just sit here and you could dot split and whatnot, but I quite like using nom for this kind of stuff, and it's good to get some practice in. So we've got these assignments, right? And we can iterate over those, and I think we can map. What do we actually have to do here? So the answer for our test is going to be 2, so let's get that in there. Let's ignore the second test so that we don't accidentally think that we should be passing there. I think in the example that we were given, 57792837. So this one, the right is fully inside of the left. In this one, the left is fully inside of the right. So it could be either one of them. So I think we actually filter map here. Actually, we're just going to filter, and then at the end, we're going to count. And this is going to be our results. So what we need to do here is do our calculation inside of this filter. This filter is going to have range A and range B, or yeah, range B. And then we do need to return a Boolean from filter. So we're taking all of the assignments that are 2 ranges. So this is a range inclusive, that's a range inclusive. The types are kind of large because range inclusive is a large word, but they're both ranges. I think we can do this logic and just copy paste it. So range A dot iter. I think we have to go into iter. Yeah. So range A dot into iter. We have all as a function. All takes a closure that returns true or false. So we'll say num, and then we just do range B dot contains num. Let A contains B equals this. And then do we really need to pass this in as a, of course, time to read the compiler output. Filter, oh right, we're not returning anything here. So let's just return true for the moment. And then contains is probably going to need to be a reference to num. And then what have I done with range? Range A dot into iter move occurs because range A has type range inclusive, which doesn't implement copy. Range A move due to this call. It's a really simple solution for this. And it's one that I encourage anybody new to Rust to use. In this case, the move is happening because we're filtering, and then I'm using range A into iter, and into iter will take ownership. So what I'm doing to prevent that is just cloning the range, which isn't a problem for us. And then I'm calling into iter on the clone so that we don't use up this range or try to do something to it while we're filtering to make it not what it should be when this whole iterator is done. So we're going to let A contains B to be this, and we'll let B contains A to be the same thing in the other direction. We'll just rename this a little bit. And if I don't do it, and I can't put 2 lets there, I'm just going to run both of these because there's no real reason for me not to. This is not a large amount of input. A contains B or B contains A. So we've now tested to see if either of them contain the other one, and we end up with a passing test. So we've got our function process part 1. We take the input as a string slice. We use the parser that we wrote with nom. We pass that string slice in, and we unwrap it to get our vec of tuples of ranges. We iterate over the vec of tuples of ranges. So each of these inside of this filter is going to be a tuple of 2 ranges, the start and the end range, or the elf1 and elf2 range. Our goal is to find out if either of them contains the other one. So I'm just running all of the code that we need to run no matter what, which is inefficient, but I don't care in this case. We don't have enough input for that to matter. So we take range A, we clone it, because if we don't clone it, then we into iter, which takes ownership of the data in range A, and filter is filtering values out. So some of these could still be used at the end of this iterator. We are counting, so we're basically throwing them away anyway, but Rust doesn't know that. And we don't want to change range A or something like that while it's still in this iterator. So to solve that problem, I just cloned, which is totally fine. We do an into iter on the clone. We test all of the items in the range that we're iterating over. So we test all of the numbers to see whether the other range contains them. If that is true, then this is true. If it's not, then we do the second one. If either of them are true, then one of them contains the other one. We filter out all of the ones that don't contain another range, and then we use .count on the end of the iterator, which returns us our use size? Yeah, use size. And we return that. So that's part 1. So now we need to get our puzzle input and actually run it. And you can see that we have a bunch of new input here. We've got 13s and 82s, and I think I saw 100 in here somewhere. So drop that input in and we will cargo run bin part 1. 500, it says. That's too even of a number for this to be correct. It is right. Okay. We we got lucky in that there were 500 of them. That made me think I was going to get this wrong and have to go back and check all my logic. Okay, so part 2. It seems like there's still quite a bit of duplicate work planned. Instead, the elves would like to know the number of pairs that overlap at all. So in the above example, the first 2 pairs, 2 to 4, 6 to 8, and 2 to 3, 4 to 5, don't overlap, while the remaining 4 pairs, 5 to 7, 7 to 9, 2 to 8, 3 to 7, 6 to 6, 4 to 6, and 2 to 6, 4 to 8 do. So instead of all, we're going to use any here. If any of the sections from, or numbers from whatever section are contained in the other range, then we win. So we're going to put 4 for our test here, and I'm going to set up the cargo watch X test, and we're not going to ignore this test because we do want it to run, and it does fail. So that's a good start, but this is going to be exactly the same code actually. So we're going to copy all of this and we're going to paste it into part 2. And the only change that we have to make is instead of all, this needs to be any. And look, our test is passing. Ta-da! I know, part 2 was so hard, right? Y'all were probably like, part 2 is taking so long. I wonder what amazingness is going to happen in part 2. It's going to be such a long part 2. No, we're done. So let's try to run it. Run part 2, 815. 815 is bigger than 500, so that's a good sign for us. And that was right. So we got part 2. Ta-da! So that did happen pretty fast. For part 2, the only change we made, so we did part 1's code exactly. The only change we made was instead of all of this needing to pass, we don't need any of them to pass. So we need any number to be inside of range B instead of all of the numbers to be inside of range B. And I guess we could do it like this too. Could just type the or in there. It's a little bit it's a little bit funny looking. But this will mean that if range A returns true that we don't execute range B. But I don't know that I care about that right now. So yeah, here's our new ASCII art here, and we get problem 5 tomorrow. I do think it's probably worth mentioning the nom stuff one more time because I'm sure it's very new for a lot of you. So let's do a recap of nom. So we've got this section assignments function, and it takes a string slice as input and returns the rest of the input and whatever type we want to parse out. So the way that nom works is all of our parser functions basically take some arguments and they all return the same function signature if you look at this. So if I highlight the first tuple, so input, you can see that every parser we use returns the rest of the input followed by whatever we were going to parse. And this is really nice for us because what it means is that we can take some of the base parsers that already exist and build them up together into a larger parser. And actually, I'm noticing here that we could do separated pair again up here. So why don't we do that? So separated pair, complete U32, tag, dash, complete U32, and that's that. So it's really nice. We get to use these higher order functions and we get to combine those into bigger, more complicated things. We get to name those parsers for each of the little pieces that we're parsing, which you can imagine that it's basically like nom versus like regexes or nom versus like writing a custom parser or something like that. And in this way, we get to build up like regular Rust functions that accept some string slice as input and return some value as an output. And then we get to combine those in more complicated ways. So in this case, our line parser is a separated pair of each of the sections, which is a range, with a tag of comma in the middle. So in this way, we've built a parser for, so going down to the absolute base, we've got parsers for U32, we've got tag of dash, we've got tag of comma, we've got new line, and we've got like the combinators, the ones that combine those for us. So we can build up 2 U32s and a tag of dash into a separated pair, and now we've got our range. We can combine separated pair again with the range on the left, the range on the right, and the comma in the middle, and now we have a line parser. And we can combine that with a separated list, which will give us the new line parser here with each of the lines as a value. So we get a vec of all of these things being parsed, and we get to build up these parsers in a very understandable, abstractable way, right? Maybe sections isn't the best name for this. Maybe I should have called this range, right? So I get to do that. Change is not the right word. I get to call it range if I want to. This is just a range parser. And we could call this something else too, right? I'm actually going to revert that because somebody's going to be watching the video and wonder why it was changed in the last 30 seconds of the video. But yeah, so we can name these functions whatever we want. We can use parsers combined with other parsers to build up really complicated parsing. And we get to like name our functions rather than looking at this giant regex and wondering how it works. So I wanted to introduce you to Nom. This is probably more of an introduction than you asked for. If you have any questions, leave them in the comments. If you'd like to see more Nom, leave it in the comments as well. If you wouldn't like to see more Nom, that's also an option. I personally like using it, so I'll probably use it again. And show me your answers. Did y'all get the problem done? In any case, have a great day, and I'll see you for problem 5 tomorrow.